So even though we have completed the CAT and we didn't have sufficient time to complete Unit 1, so I don't want to skip any portion of Unit 1 because it's a bit different about the architecture. So I'll try to complete Unit 1 by today. And as I told you, subsequently, Unit 2, 3, 4 are very easy to understand, and syllabus-wise also they are very less in content. So we'll try to finish off Unit 1 by today. And we have stopped with last class about the image rejecting configuration of receivers. So there are two things where trade-off has to be obtained. One is image rejection or channel selection. Either you reduce the noise or select the proper signal. So that is the two options available. And we are going to see about what all the possible image reject architectures available, which is going to ensure that we are going to reject the image effectively rather than selecting the channel, because selecting the channel we have to put a lot of filters in the circuit, which might not be feasible when you go working in high frequency. So we rather look at image reject architecture, where we'll try to minimize the image frequencies in our received signal. So we have seen in the last class, we have come up with a equation where we have seen involvement of signum function. So we have seen the positive frequencies multiplied by minus j and negative frequencies multiplied by plus j. So this is seen in frequency domain. So you know minus j means a phase shift of minus 90, because minus j comes in your lower part of y-axis, and your x-axis positive is your reference. So when you take that as your reference, minus j is phase shifting by minus 90 and plus j is phase shifting by plus 90. So effectively you need 90-degree phase shifter. You know sine and cos, however you phase shift by minus 90 or plus 90, you will get back the other signal, right? So effectively I need to shift by 90 degrees. And in signals we have a beautiful transform which is going to shift by 90. That is going to be called as Hilbert transform. So if you give a signal pass through a Hilbert transformer, the output will be 90-degree phase shifted version of the Hilbert transform, phase shifted version of the original signal. So that is going to be the Hilbert transform. And circuit wise, if you see, we can implement a 90-degree phase shift using high pass and low pass filters. You know, a single RC is going to provide a phase shift of 90. So we can use high pass and low pass to generate two different combinations where you can pass the same signal to both high pass and low pass filters. That is what is shown here. You can see in the diagram. The input signal is given to one C in series R in shunt. This is going to be your high pass filter, and this is going to be your low pass filter. So we are going to pass the same signal here, and you can see low pass filter will allow the will attenuate the high pass filter is going to attenuate the low frequency, and it is going to allow the high frequency. At high frequency, the gain becomes constant. And low pass filter, you see, it allows the low frequency and it attenuates the high frequency, and the cutoff frequency is given by 1 by 2 pi R1 into C1. And you can see the phase shift of 90-degree maintained between HPF and LPF. So if you find the phase shift between the two circuits, between the two signals at Vout1 and Vout2, they'll be always out of phase by 90. From the diagram, you can see a constant phase shift of 90 is maintained between HPF and LPF. Okay, so that is how we are going to generate this phase shift of 90-degree between the two signals. So whatever received signal I'm going to have, I'm going to pass through LPF and HPF, and the output, the two outputs are going to be always out of phase by 90 degrees. So that is what is illustrated in the previous case. In case if we are going to work at a very high frequency, then realizing capacitor is going to be very, very difficult. So in that case, that is not possible. So we are going to go for the conventional mixing. So we are going to conventionally mix your received RF signal with the local oscillator, which is phase shifted by 90 degrees. So this architecture we know already, we have seen. So we are going to have the RF frequency, and I'm going to use this LO. And one for the in phase, it will be going it as cos, and for quadrature phase, this LO will be shifted by 90. The cos omega t minus 90 is going to be sine omega t, and I am going to produce in phase and quadrature phase components. So you can see the diagrams here. So this is your RF signal, and this is going to be your local oscillator. When you are going to mix, you are going to get these two signals. So this is going to be the IF frequency. This is going to be the I channel. This is going to be the Q channel. And as we say, the I channel is multiplied by two positive components because for the Fourier transform for a cos signal is going to be two impulse signals. And for sine is going to be one positive and one negative because cos is an even signal, sine is an odd signal. And when you add these two things, you'll get back your original signal. So one way of realizing this image reject receiver at high frequency is going to use a local oscillator with the quadrature phase shift or 90-degree phase shift between the two signals which are fed to the in phase arm and quadrature phase.